Okay, so here's a set of graph of 5 cosecant 2x minus pi over 6. We obtain it by graphing 5 sine 2x minus pi over 6. Just replace cosecant with sine. We know how to graph those already, and then we fix the cosecant to touch the peaks of the mountains and the bottoms of the valleys and have asymptotes where sine crosses its midline. Similarly, we can sketch secant to touch the peaks and valleys of cosine. Just do the same function with the same numbers, replacing secant with cosine. Any others that you'd like to see out of that? Was there a request to do some of the earlier sketches? Just for looking back on the old videos.
Yeah, that'd be great. If we could just look at the original notation for sine and cosine and just go over the stuff like amplitude and all that again, just make sure I have it right.
Okay. If you have a sine or a cosine, this is what you do. You take the 5 steps here. You compute the amplitude as the value, absolute value of A. The period is 2 pi over absolute value of B. Generally, we don't need this absolute value because we're going to assume B is positive. I'll do one more with secant. How about? And that'll do this for cosine. You flip it if A is negative. Then you have a phase shift C over B and a vertical shift D. Whenever you write an A sine bx minus C plus D or an A cosine bx minus C plus D, you do these 5 steps. All right. So let's try this one. And then if you have a secant or a cosecant, put that off the screen for you guys online, didn't I? So I'm saying these 5 steps right here. If you have a secant or a cosecant, you draw the same thing for sine or cosine, follow these 5 steps, and then gets the reciprocal by touching the peaks and valleys. So suppose I said this one, sketch y equals minus 2 times the secant of pi over 3x minus pi over 4 plus 2. Suppose I have that one. What I do is I say to sketch secant or cosecant, I'm interested in first sketching with the same numbers the reciprocal function, y equals minus 2 cosine pi over 3x minus pi over 4 plus 2. So I'll first sketch this one, and this has all the tricks in it here, right? So this will be an advanced problem. What I'll do is I'll say, here's A, whatever multiplies the trig function. Here's B, whatever multiplies x. Here's C, whatever subtracted from px. And here's D, what's ever added on the end. Right? Being added in front or on the end, just what's added to the whole thing. Some books I could put it in front. To sketch that, I do these 5 steps. I do the amplitude. Absolute value of A is 2 in this case. Amplitude is always positive. The period. For sine, cosine, secant, and cosecant, the period is always 2 pi over B because the natural period of those functions is 2 pi, and when you put it in here, it scales it horizontally by 1 over B. So you get new period 2 pi over B, 2 pi times this scaling. And 3, this one we're going to say, 2 pi over 3 in this case. You be careful with your fractions, right? This is 2 pi over 4 over 1. Careful with your quotients, over pi over 3. And now top times bottom is 6 pi over middle times middle is pi. Pi's cancel. This has period 6. It does not have to be a multiple of pi. If B has a pi in it, it can cancel out like this. The flip here is yes, because A is less than 0. Negative 2 is less than 0. Right? So and we're only going to do vertical flips. You can do a horizontal flip if B is negative, but we're going to avoid that by whenever we see B negative, use the even or odd property to take it out. So now for the phase shift for this wave, we won't talk about a phase shift for the other functions, only for sine and cosine because they're waves. Phase shift will be C over C over B, always. We figured that out from our graphing strategies from algebra. Is whatever's subtracted here, it's plus pi over 4. Over B is pi over 3. All right, and so you take top times bottom, 3 pi over middle times middle, 4 pi. 3/4. The pi's canceling. Now finally, I need the vertical shift is whatever's added on the end, D. Two. To do these 5 things, I like to do these last 2 first because it's just easier that way to move the graph and then stretch it around the shift point rather than try and stretch it and then shift it. But you can do either. Move this over. So now let's get the cosine of these 5 steps. I'll first do the shift point. It's 3/4 over and 2 up. This point right here. Then I'll go to the amplitude and say the amplitude is 2. The midline will go through the shift point. And then the guidelines for the cosine, the amplitude up 2 and the amplitude down 2. So we get guidelines at y equals 0 and y equals 4. Do these 2 and then 1, 2, 3. And now the cosine does not go through the shift point. The sine goes through the shift point because the original sine goes to the origin, but the shift point is where the origin moves. And the cosine doesn't go, the natural cosine doesn't go through the origin. The natural cosine looks like this. Starts at the top. So this will start at the top if you have an unflipped cosine. When you have a flipped cosine, you start at the bottom below the shift point. So flipped cosine start at the bottom guideline. Below the shift point. Then I have to go over 1 period. That's 6. So if this is 3/4, I need to go a whole lot more than that, right? See, am I still on here barely? So I got 3/4 plus 6, right? I'll go over 6 units from here. 1 period. And now this point that was on the graph will be here at 3/4 plus 6, the shift point plus 1 period. Let's see, if 24/4 plus 3/4 is 27/4. So that'll be right here. And now what I want to do is from the cosine, draw 1 wave, all the way up to the top, all the way back down to the bottom, completing 1 period. And it should touch the top halfway through here, right? Something like that. Oh, it's tricky to draw. All right. So 1 complete period from here to here, right? That's the cosine function. And then you can make it repeat, right? I got finally, with a lot of work, this is a hard one, right? Y equals -2 cosine pi over 3 x minus pi over 4 plus 2 sketched. And you can get 5 exact points, right? This one is 3/4 and the coordinate of the bottom guideline 0. This one is 27/4 and the coordinate of the bottom guideline 0. This one has to be halfway between. What's halfway between 3/4 and 27/4? It's halfway between 3 and 27, right? Well, they're 24 apart, so it's 12. It's 15/24, right? Halfway between 3 and 27 is 15. So this will be 15/4. The top guideline is at 4, so you put the top guideline coordinate there. And then it crosses the midline. If I sketch this correctly, it's a little off. Halfway between 3/4 and 15/4. What's halfway between 3 and 15? Well, they're 12 apart, so it's 6. 9/4. 9/4 of the quarter of the guideline is 2. And then here would be halfway between 15 and 24, 27 would be 21/4. There's 5 exact points on the cosine, if I want to sketch that. This is an example of sketching cosine. I actually asked for that. Now, how do I sketch the secant with the same numbers? All I have to do is wherever the cosine crosses its midline, right here, I don't even need to plot a point, I draw an asymptote. And the secant, its reciprocal function, will then come down and touch the peaks of the cosine function that has the same numbers and the bottoms of the valleys. And so it'll be a U shape up, U shape down, U shape up, U shape down. This is the graph that we wanted in the first place. Y equals -2 secant pi over 4, not 3x. Minus pi over 4 plus 2. Okay. Now sketching secant and cosecant. And then finally, if you want to sketch tangent or cotangent, it's very similar. You follow the 5 steps the same, except that the period is pi over b instead of 2 pi over p, because the cotangent tangent have natural period pi instead of 2 pi. And then you draw a wiggle instead of a wave. Want to see one of those? Is that? I have enough of those. Then you can try and fit the graphs to the functions to the given graphs also. So if I said, I'll do this one real quickly because I didn't see a lot of interest. If I want to sketch y equals -2 tangent 3x, I'll do one that hasn't got a whole lot of things. I'll do the same 5 steps. One, I'll do the vertical stretch, which I now call a vertical stretch because it's not a wave, it's a stretch is absolute value of A is 2, right? And B is 3 here. Evidently C is 0 since I'm not subtracting anything, and D is 0 since I'm not adding anything at the end. So 2, the period for a tangent function is pi over B. In fact, let's do the last trick I said here. What if you had -3x here? So B is negative. The period is always a positive number, so it's pi plus 3. But in order to sketch this, what you do usually, instead of putting a negative B in there, how can I get rid of that negative? For tangent is an odd function. So I can rewrite this and pull the minus out. I can say minus 2 in front. It's -2, and then tangent is odd. Minus tangent plus 3x. So you can pull the minus out here and put it in front of tangent. Now these minuses cancel, and you've got 2 tangent 3x. Easier to draw. Now B is positive, so the vertical stretch factor is 2. A is positive now. And the period is pi over 3. And now I've changed it to a plus 2 here. I just take the now that this is a plus 2, there's no flip. So if B is negative, just pull the minus out and put it on here into A and sketch this function instead. And now for that, it's pretty easy. For C over B is equal to, well, C is 0. It's 0 over 3. So it's 0. And 5D is equal to 0 because there's nothing added at the end. And so the shift point is just 0, 0. We didn't shift it at all in this case. All we did was we stretched it in the vertical and horizontal directions because of the 2 and the 3. For tangent, what you have to do then is through the shift point, if it's not flipped and you draw it up through here, like the natural tangent looks like this, with asymptotes, pi over 2 and minus pi over 2. You need to have those memorized, actually. They use them a lot outside of class, mostly the sine, cosine, and tangent. This is y equals tangent x. And it's got these important points halfway between the x-intercept here, asymptote, you get pi over 4, it's 1 unit up. And here at minus pi over 4, it's 1 unit down. Those are easy to remember. That tells you how steep it is. So we'll draw it up like that with the idea that what we did is we stretched it in both these directions, but it still goes through the shift point at 0. Now, since the period has changed to pi over 3, what you do is you go half a period on each side, pi over 6 here, minus pi over 6 here. So we said to sketch the tangent, go through the shift point, go half a period on each side, and sketch this towards the asymptote in each direction. If it's flipped, right, you turn it upside down. Since it's unflipped, it'll go up to the right and down to the left. There's the wiggle. Then it repeats over and over. Since the period is pi over 3, this next x-intercept will be at pi over 3. And then here, since this is pi over 6, if you add a period to it, this will be pi over 6 plus pi over 3, which if you do the fraction and quotients, it's pi over 2. And so you can sketch more and more periods of this function. And then it's just how much is it stretched, I wonder? Well, halfway in between 0 and pi over 6 is pi over 12. And what you do is you use the stretching factor here. The stretching factor is 2. So it goes to here at pi over 12, 2. It's halfway between the intercept here and the vertical asymptote. Go up to the stretching factor on this side. And then you go down to the stretching factor on this side. So this one would be minus pi over 12 minus 2. That tells you how steep it is. Now what we want to do also is be able to look at a graph and figure out what fits it. We did that with sine and cosine. Let's do that with a secant function here with cosecant. How about this one? Find the equation of the trig function indicated here. This is similar to one of your homework. Suppose that you have, go down to 2, up, negative 2, maybe that's x equals 0, x equals 4, and x equals 6 for the asymptote. How can I find the equation of this trig function? Then it repeats over here. It's another U shape down over here, U shape up over here. How do I find the equation from the graph? What you need to do is figure from the 5 properties the 4 letters, right? So what we did to sketch these in the first place was consider the reciprocal function. Let's consider the reciprocal function of this one. And we can make a shift point, has to be on the midline. So here's the midline, evidently, is the x-axis. I need a shift point that's on the midline. And what happens is the cosecant has an asymptote on at the origin, so we can choose the shift point here on an asymptote. Secant has the shift point where you have a bottom or the top of the U shape, so we can pick a shift point here and use secant, but you have to choose it where there's a bottom of a valley or a peak of a mountain or an asymptote. So one of these kind of points has to be the shift point. This other asymptote here. Okay, so I can pick any of those for the shift point. And if I pick this one, I have to use a secant function because it's where the natural secant looks like this. There's the cosine, and the secant comes down here. When you have the natural secant with the shift point at 0, then you're at the bottom of a U. So you choose secant if you're going to choose the shift point over here at the bottom or the U or the top of a U. But the cosecant, being the reciprocal of sine, cosine, and this is secant. This is sine, and its reciprocal cosecant. The shift point is an asymptote for the sine, or for the cosecant, and so here we can think of this one. If we want to think this one as a reciprocal, we need to draw this function here that just touches the peaks and valleys. We can use the sine. If we make this the shift point, it goes through here, through this point of the origin, like the sine. Or we can think of this as the shift point if we want to think of a cosine, so it's at the top of the shift point. The easiest thing to do for this one will be use cosecant, and then the shift point could be 0, 0, right? So choose 0, 0 for the shift point. Then, since sine goes through here, sine and cosecant. If we would have picked this one, then we'd have to, for the shift point, we'd have to use cosine since it has a maximum here, and secant to touch its maximum. But you can use either one. When you get these U shape up, U shape down, you can fit it either with a cosecant or a secant, just like you can fit a wave with either a sine or a cosine. And there'll be an infinite number of solutions, just the same. So we draw this reciprocal function and say, here's the shift point. What's the equation of the reciprocal function? Well, it goes through here with period 6. So amplitude is 2. Because the absolute value of A is 2. Since it goes up through the shift point, it's an unflipped sine, right? It goes up through the shift point. Unflipped sine wave, sine function. Absolute value of A is 2, and since it's unflipped, that says A equals plus 2. Then the period is 6. Period is 2 pi over B. So if we take reciprocals, this says 1/6 over 2 pi, multiply by 2 pi. What's online? Multiply by 2 pi, and you've got 2 pi over 6 is equal to B. Evidently, B equals pi over 3. So there's B. You get B from the period, A from the amplitude. And there's no shift. So shift point 0, 0. C over B. B. See how much easier we made it by picking the shift point 0 when we can. Now it tells me immediately C is 0, so that C over B is 0, and D is 0. So definitely C equals 0, D equals 0. And the wave here, the blue one, has the equation y equals A sine dx minus C plus D with this ABCD, it's twice sine of pi over 3 x minus 0 plus 0. It's just 2 sine pi over 3x. That's it. That means that the red one is the reciprocal function. It must be the same numbers. So cosecant is 2 cosecant x. So see the graph like this, think of the reciprocal function, which you've already done. How do we fit that? And then just, when you find that, change sine to cosecant or cosine to secant. Finally, you can check these answers on your calculator. If you have your calculator, you might get it out. Right? So just bring my best calculator for this stuff. Calculator check. The calculator doesn't so easily find these 5 points exactly, but it will check approximately. In some cases, you can check the exact points pretty nearly. But to use the calculator, this is what you've got. You've got a big screen up here, right? You've got the 5 buttons, y equals, and then window. There's a zoom and a trace. Zoom or traces first. Do I have a TI-84? Zoom is first, okay. Zoom, trace. And so below the big display, you see those 5 buttons. And now graphing these things is as easy as 1, 2, 3. You push 1, the button y equals over on the left, just below the window. This is the window. And then you enter the function. Right? Well, how do I sketch this one? Y equals 2 cosecant pi over 3x to check if I'm really getting that graph I'm supposed to. Well, it's reciprocal, right? So instead of sketching y equals 2 cosecant pi over 3x, I enter, and here's what appears on the screen when you push the y equals. It says y1 equals, y2 equals, y3 equals. And you can enter multiple functions and graph them all at the same time, right? So you enter a function here and it'll plot, two ones will plot in one color, enter a function here, it'll plot the next function. So you could plot sine and cosecant both. But to sketch just the cosecant, then it'll come up with y1 and you just enter 2 divided by sine pi is gotten by second caret. Pi is up above here. Divided by 3 times x. And the x button on the calculator says x tau theta n. It doesn't say x on it on the TI-84, at least it says x tau theta n. And if it's in rectangular mode, which is the default XY plotting mode, when you push this button, x will come up. If another letter comes up at some other plotting mode, you have to reset the plotting mode. The other thing you have to do is put it in radians mode. We've been doing all our sketches in radians. That's what's useful in higher mathematics. If you don't put it in radians mode, it'll give you some kind of, sometimes it won't even show up. And you say, why isn't it there? That's because it's trying to plot one period in whatever, 360 degrees. And so it just does a straight line. It looks like it's not going anywhere unless you plot out to 360. So let's see, 3x, and then I'll close my parentheses on many of these calculators, depends on the calculator. And then you push, you don't have to push enter even. This just puts it in the calculator. So you push y equals, this comes up on the screen, you enter these things, and what appears up here is 2 slash, that's the computer programming symbol for divided by sine, and it inserts a parenthesis automatically. Second caret puts a pi on the screen, and then divided by 3, it'll put slash 3, it puts this symbol for the programming divide on there, and then times x, will put an asterisk on x. When you push this one, it puts x, and then there's your closing parenthesis. This is what you enter here. You push the buttons to enter that. And you say, wait a minute, isn't that pi divided by 3x? If you want, you can put more parentheses to feel careful, but remember what it does is it multiplies and divides from left to right with equal precedence. So we'll do the divide first, which is what you want, right? You want pi divided by 3 and then multiply the result times x. So this is actually correct without parentheses, but you can put in parentheses if you want. Convince yourself or something. This will do it without any more parentheses than that. Any questions on that so far? Looks very complicated for a calculator, right? What you really do is you don't memorize all these keystrokes. You memorize you have to push second, and this one with the pi over the top to get pi. Otherwise, you got to enter 3.14159 by hand or something like that. But just make sure this comes up. You push y equals and enter 2 divided by sine pi divided by 3 times x. Right? Close it. Now you go to the next step. You push window button, which is right here next to it. And you enter the plot limits. What happens when you press the window button is this screen changes. And it says X bin, X max, X scale, Y min, Y max, Y scale, and then there's another number below that you don't care about. It's X res. We don't need that. SCL for scale. Equals. On these, you have to enter all the numbers. The first one, you only enter as many functions as you want. But this is the minimum value of X for plotting. So maybe we'll plot it from 0. So we might put 0. And then we'll arrow down. There's the arrow keys on your calculators. All right, this is not an 84, but it's an old TI 89. But when I said the math majors might want to go higher than engineers. Push the down, here's the 4 arrows, push the down arrow. Enter 0 for X min. And maybe I want to plot it out to, what's the period here? It was 6. So I can plot it out to, maybe actually, yeah, it's out to 6. So I want to go from, maybe I want to show just one period. I might plot from 3/4 to 27/4. Why don't we do that? We could just enter here, like 3 divided by 4, then arrow down to the next line. Down arrow. And then enter 27 divided by 4, down arrow, and etc. And what it'll do, it'll plot. This one puts in X min equals 3/4. This one puts in Y X max equals 27/4. What you want for X scaling factor is how far you want between the tick marks. If you want to put every quarter here to try and check these are exact, you might push 1 divided by 4. Y min, maybe we want to plot from 0 to 4, so we can see the wave goes from the bottom of the top to the top of the screen. So we can put 0 here and 4 here. Y scale, let's plot every unit, right? 1, 2, 3, 4. So 1. And so if you put these numbers for all the rest of those on that screen, just by typing more keys here, that's the ... Now you're all set. And now the last thing is you just push graph. And what you should see is a nice graph that looks just like this thing, the original function that we had, going between the bottom of the top of the screen plotted from right here, we set it up that way to right here. You should see it go from the bottom to the top, just like that on the screen. With these tick marks, every quarter unit, there'd be a lot of them. It doesn't label the tick marks, but you can check it pretty carefully that way and see if it's. Okay, there's doing it on the calculator to check it. Comments on that one? Once you reiterate, this seems a lot easier. That's a lot of keystrokes, right? But if you remember it this way, it's 1, 2, 3. 1, y equals and enter the function. 2, enter the plot limits. 3, push graph. That's it. All right, so y equals window graph. And we just have to enter the stuff. Now the zoom is if you can press that if you want to zoom it in close and look at it up close. You don't really need that. Trace it, we'll put a little asterisk on here. And when you click the arrow keys, that asterisk will move around here and give you the coordinates. That's not really useful, but you can use those as you wish to kind of get decimal places on points on there. All you need is these three. Okay. All right, that's going to finish the section then. And what I want to do the rest of today then is inverse trig functions. This will be the next section. Now, I need to give you the homework on that one. 6.2 then. Uh, 6.1, we said do 1 through 6, all but the last one. And then out of 6.2, we also want all but the last one there. 6.3 first trig function requires actually a good algebra review to understand it. So even though I won't test you on these algebraic aspects, these are absolutely key for understanding what you're doing, and I think for being able to memorize. Without it, it just seems like in algebra, a function y equals f of x has what we call an inverse relation, not necessarily a function. X equals f of y. Remember finding inverse functions in algebra? How did you find an inverse function? For y equals f of x, you wrote x equals f of y and you solved for y. Does that sound familiar? Oh, who remembers that? To solve an inverse of y equals f of x, you put x equals f of y and solve for y. And here's why. If this is y equals f of x, maybe. And you call this x equals f of y. Carefully here. What do we know about this graph? We just interchanged x and y to get these two, right? That means it's equivalent to interchanging the axes. They are mirror images of each other across this line that splits the axes, which is the line y equals x, right? Now, if that means, since you're interchanging x and y, if you have any point here, a, b, on y equals f of x, there's going to be a corresponding point over here, b, a, on x equals f of y. And because you just interchange the coordinates and it's a flip, right, there's a symmetry here. It's the same distance across, same distance here as over here. And now what happens, if we also call this, we'll say AKA, what does AKA stand for? Yeah, also known as, like Muggsy or something is the gangster's name, also known as Muggsy. Anyway, y equals f inverse of x. We'll also call it the inverse function if this inverse relation is a function. How do we know it's a function? We're given that this one's a function. Y equals f of x. How do we know the inverse relation is a function? Don't, it might not be, right? Like if I take the parabola, y equals x squared, and I flip it over the line y equals x, this doesn't pass the vertical line test. The parabola was a function, but when I flip it over the line y equals x, the inverse relation, the horizontal, lots of vertical lines that intersect it more than once, right? Graph in the plane is a function if and only if no vertical line intersects it more than once. So it may or may not be a function. In this case, it looks like we got one here. No vertical line seems to intersect that more than once. Here's vertical lines intersect it not at all. That just means the function's not defined there. But if no vertical line intersects it more than once, then it's a function. We might get lucky when we flip it. Maybe we'll get a function, maybe we won't. This occurs if and only if you think about it, the original function, no horizontal line intersected more. Right, because when you flip a horizontal line like this over the line y equals x, right, it becomes a vertical line. So an inverse relation gotten by flipping a function over this line y equals x to get x equals f of y will be a function if and only if the original function had no horizontal line intersecting more than one. Such a function is called one-to-one. So if this is a one-to-one function, then this one will be a function. And no vertical line will intersect it more than once. All right, so that's the trick. And now I'm going to go and remind you something from algebra. More from algebra. Now, in this case, we can label it as y equals f inverse of x, not just say x equals f of y. That always works, right? But if this no vertical line intersects this more than once, then this defines y as a function of x. So we'll write this notation for the same curve, f inverse of x. It's a rule that each x assigns exactly one y. We'll just say we'll call that f inverse because we got it from f. And by the way, when this f inverse of x, it does not mean 1 over f of x. So this is not the same as 1 over f of x. This is a conflict of notation in mathematics. If we write 2 to the minus 1, that means 1 over 2 to the 1, right? Or 1 over 2. It's the inverse, multiplicative inverse. But this inverse on a function does not mean the multiplicative inverse. It means the inverse function gotten by flipping. So this is not 1 over f of x. It's this graph here. Now, in this case, when the inverse was when the inverse relation is a function, y equals f inverse of x, we give the notation. What do we have? We have that f inverse of f of a for any point a b on the function What? Well, f of a is b, right? If it's on the function, then f of a is b. This is f inverse of b. But then we said that you define the inverse relation by reversing the pair and getting ba. So if this is on the inverse function, f inverse of x, I can put in b and get out a. So f inverse of b is a. And you get this result that f inverse of f of a is actually equal to a. Any a on the ab on the function. Also, if you take f of f inverse of b, any point ba on the inverse function, or ab in the original function, you put in b to the inverse, you have to get out a. But f of a is b. Now you see why it's called an inverse function. It undoes the original function, right? If I take f of a to get a number b on the function, I take f inverse of that and I get a back. It undoes what f did. And also they undo each other. If f inverse of b gives me a, then f gives me b back. So that's why it's called the inverse function. It undoes what the original function did. These are key relationships. So we'll define an inverse function this way because it leads to this result. And you can leave out the intermediate step if you want. Memorize that. Now, maybe this looks like something in algebra. What kind of functions in algebra does that look like? This might be y equals 2 to the x, right? What is the exponential function y equals 2 to the x? That went up like this. What would this be in algebra? Inverse function is exponential function base 2. What the inverse function is, this is what's hard to remember. It's the hardest part of the course, I think. Yeah, awesome. Yeah. It's y equals log base 2 of x. The log base 2 of x, we'll say here's an example. If f of x is 2 to the x, the inverse function, log base 2 of x, and what you get from that is that 2 f of f inverse of f of x log base 2 of 2 to the x, and remember they undo each other, they give you x back. That was the reason you introduced logarithms, was to undo exponentials. This is very important in finance. Your bank interest grows exponentially, and so you can calculate how much money will I have in 20 years, but if you say, how long does it take to get $1 million, then you need to find out how much time before you have that much money, then you have to use logarithms. So it's real important for being able to do exponential functions backwards. Your bank interest grows exponentially, but to find out where the exponential is going to be, you have to use logarithms. And so they undo each other, and then they undo each other. This is f inverse of f of x. If you take f of f inverse of x, then you got 2 to the log base 2 of x, and they undo each other in this order. You also get x back. So those were real nice examples, and you don't need to know any of this. But if you don't know this, then all we do with the inverse trig functions won't make a whole lot of sense. But you could rote memorize it maybe. So there's the algebra. Now, with a little bit of time left, hopefully, we can apply it to trig functions. How can we find the inverse of a trigonometric function? See how important it was for exponential functions to be able to take an inverse. Now you realize, right, that the exponential base 2 and the logarithm base 2 are actually the same shape. You just flip it over the line y equals x, one to get to the other. We're going to do the same thing with trig functions. Inverse trig is slightly more complicated. But follows this concept. So 1 for y equals sine of x. What is the inverse sine function. Right? So I sketch the sine function, and I remember it looks like this, right? Oscillates between plus and minus 1 with this minimum at minus pi over 2 and this maximum of pi over 2 pi, 2 pi, 2. And I realize immediately that for this function, all this inverse stuff doesn't work. Why? Why can't I take an inverse of this function? It's not 1-to-1. It fails that horizontal line test, right? If I take this one and flip it over the line y equals x, it's going to look like this. It's going to wiggle back and forth. It won't be a function, right? Be careful of real old trigonometry texts. I said you can go back and look at trig books. They've been good a long time, but this is one difference in the old notation. They would call this the inverse sine of x, and it's not a function. It's what we call a multi-valued function or an inverse relation. And right, it fails the vertical line test. If you give me x equals pi over 6, what's arc sine here, inverse sine? Oh, it could be that y value or that y value or that y value. It's a multi-valued function. So in old books, they'll if you use this for inverse sine and go more. Instead, what we want to do, since this has no inverse, fails horizontal line test, it's not 1-to-1. Flip it. Function. But if we were to take a piece of it, let's take the longest piece we can near the origin, but no horizontal line intersects more than once. We could take this piece right here, which goes evidently from minus pi over 2 to pi over 2. Well, let's instead flip this piece over y equals x and get its inverse. I'll plot down below, keep the clutter down. So this is pi over 2 here, right? And it goes up to 1 here. This is the point pi over 2, 1 on the sine function. This is still y equals sine x, just a piece of it. And then over here, we had minus pi over 2 minus 1. And then it goes through 0, 0, it's the sine. And let's flip just this piece over the line y equals x, and it turns out, you can show in calculus, it's actually tangent right here. What are these points? Figure it out if you're clever here. What we did was we flipped this over the line y equals x and got, instead of y equals sine x, we got x equals sine y. Since we're interchanging x and y to get the inverse, that was the concept. All we have to do is reverse these ordered pairs. This is the point 1 pi over 2 instead of pi over 2, 1. You reverse the pair, right? Instead of AB, you get BA. And this is the point minus 1 minus pi over 2. Reverse the pairs. And 0, 0 when you interchange them, it's still 0, 0. So this one goes to the origin. And this is the one we call inverse sine of x, even though it's only the inverse of a piece of the sine function. So the sine function is not invertible. There is no inverse for the whole thing. But this piece of it is, and we'll call that the inverse sine. Or it also has this notation, arc sine x. Means the same thing. And then in those old books where you had the wiggle with the inverse sine function, what they do is they'll put a capital letter here and a capital letter here. This is the piece of the inverse function. They were trying to preserve notation. If you put the function with a little minus 1, it meant the inverse of the whole thing. But it's too complicated, I think, for everybody to remember. So now this will mean the inverse of the piece, and this will mean the inverse of the piece. And all the modern textbooks, they do this, including yours. All right. So that's what it means. The inverse sine function is only an inverse of a piece. Then it means it doesn't invert the sign on the whole interval. This interesting difficulty. Now what happens is if you take the inverse sine of the sine of any angle x, what are you supposed to get back if you take f inverse of f of x? Well, you get your x back, right? That was the whole idea of the inverse function, right? F inverse of f of a was supposed to give a back. It does so if you start on this piece here, right? This is why you need that preamble there. Minus pi over 2 less than or equal to x less than or equal to pi over 2. This works because this is the piece of the sine function you flipped, right? But you'll get something else otherwise. There's the disclaimer. Since you only picked a piece of the function, the inverse sine will only undo the sine for these values of x that came off that piece. But if you do in the other order, f of f inverse of x is also supposed to undo each other. X back. The curly brace again. And it does actually, because right, this thing here, if you flip it, it's all on the sine function. The sine function has more, so the sine always undoes the inverse sine. But the inverse sine is only defined for certain numbers. What's the domain of inverse sine? What the domain of a function is? It's all numbers you can put in, all values of x. Now for the sine, it was all real numbers, right? You give me any x, I can tell you what the sine of that angle is. You know, for any x, there's a y plot, but not for the inverse sine. That's this thing here. It's only plotted for x values between -1 and 1, right? That's the biggest x value, the smallest one. So the domain is just -1 less than or equal to x less than or equal to 1. If on your calculator you put in arc sine of 2, it will give you a domain error. It's a domain error. And what it's telling you is that, right, this arc sine is telling you what sine has that angle. It's doing the reverse problem, right? The sine tells you what's the sine of the angle. The inverse sine tells you what angle has that sine. It's saying, when you put an arc sine of 2, you're saying, what angle has sine equal to? Well, there isn't any. Sine just goes up and down between plus and -1, and y is never equal to 2. So, it says it's not in the domain. But here's the formal picture. Right? It's only plotted between -1 and 1. You can only put in those x values. And then what's the range? Range is all the y values that can come out, right? But the smallest y is -pi/2, and the biggest y is pi/2. And it's just backwards from what you took here. Whatever the domain and range is of this piece, then you flip it and then change the domain the other order. So -pi/2 less than or equal to y less than or equal to pi/2 y values that can come out. So it can only give you angles of the first and fourth quadrant, right? Between -90 degrees and +90 degrees, and you can only put in numbers between -1 and 1. But then it has this property that will invert it if the angle's between plus and -90 degrees. And then this one works always whenever it's defined, but it's only defined between -1 and 1. So it's x between -1 and 1, the inverse sine gives you back, sine of the inverse sine gives you back x, but then you get undefined. This inverse sine is undefined otherwise. X is bigger than 1 or less than -1. So there's the drawbacks to this thing. And now we can actually calculate some inverse sines by hand when the number comes from a special angle. So when x sine special angle, multiple pi/6 or pi/4, we can evaluate inverse sine of x or arc sine of x by hand exactly. Otherwise, we use the calculator. And ask this very interesting question now. suppose I said, what is the inverse sine minus a half, for instance? Here's how you find it. You say, this question is asking, the verse of taking the sine, what angle theta has this sine? That's what it's asking, but it's a little more tricky. It's a little trickier than that because there's an infinite number of solutions to this mentioned before. All coterminal angles have that same sign, but this asks specifically, right? The arc sine gives you the angle, always gives an angle between minus pi over 2 and pi over 2. Those are the only angles it can output. So we're really asking what angle between minus pi over 2 and pi over 2 the sine equal minus half. That's what the arc sine of minus a half is. What angle in this range of angles, first to fourth quadrants, has sine equal a half. So you can use the unit circle just like we did previously and say, here's the unit circle, minus 1, 1. And if I want sine theta equal a half, that's the y coordinate, so I go down to minus a half. Go down to minus a half here. Find all the points on the unit circle that have that y coordinate. Oh, there's 2 of them. So there's only 2 possible terminal rays, and which one do I want? I have to restrict the angle between minus pi over 2 and plus pi over 2. It has to be in here. So I throw this one out, it's in the wrong quadrant. And furthermore, I can't go around this way. That's not the right angle because that's bigger than pi over 2. I can only go this way, minus pi over, well, what is it? Since it goes down to minus a half. This side length is a half. This side length is 1 because if the unit circle, you recognize on a right triangle, the Pythagorean theorem will force this to be square root 3 over 2. This is minus pi over 6. It's a 30-degree angle in order to make this triangle. So if this number comes from a special angle, we recognize, oh, there is a special angle that has sine equal minus a half. What is it? You can figure it out in the unit circle and it's minus pi over 6. That's how you do these. You ask this reverse. Right? Rather than assign these, I think I'll pick these up next time. Do a bunch more examples. And we can also. The good news is we're not going to do inverse cotangent, secant, or cosecant. Thank you for coming in today. 6.1 and 6.2.